Hello everyone. Today we are going to discuss the concept of thermal stresses and composite bars. So before we jump into the concept, I think it would be a good idea if we recapitulate the concept of thermal stresses first before we get into the topic of thermal stresses and composite bars. Okay. So I have already made a separate video on thermal stresses in bars, not composite bars, simple bars, why thermal stresses actually come in the first place. You may also want to check that video. I can give the link in the description below. Nonetheless, if you look at at a bar, say just consider a bar, and let me define the geometric properties of this bar. Let us say that this bar has got a length of magnitude L, it has got a cross-sectional area of magnitude A. So I have clearly defined all the geometric properties. Let me define the required material properties. This bar is made up of material that has got an Young's modulus value of magnitude E. That's one material property that is required. The other material property that would be required is alpha, which is the coefficient of thermal expansion. Now, what I'm going to do is I'm going to increase the temperature of the bar in a very, very uniform fashion. The word uniform is very important here in this context. The reason why the word uniform is very important is because if you increase the temperature in a non-uniform fashion, then there will be thermal stresses that will crop up, okay? So I think the word uniform is very important. So I'm going to increase the temperature of the bar, throughout the surrounding, in a very, very uniform fashion. As a result of which, what's going to happen is this bar is going to expand on the right side. Let us say that the bar expands by an amount del L. The bar is not going to expand on the left side because there is a constraint there. So whatever expansion is prevented on the left side is actually produced on the right side, besides the expansion that would actually happen on the right side, okay? And this is going to be a uniform increase in temperature throughout the length of the bar. So in this case, because there is nothing to prevent the expansion, there is not going to be any thermal stresses here in this context, okay? So thermal stresses crop up in the first place only when the expansion is prevented or hindered. So two reasons when the thermal stresses would happen. The first reason when the stress would happen is because when you arrest the expansion, when you arrest the expansion, there will be thermal stresses, okay? And the second reason why thermal stresses would occur is because when the temperature distribution is not uniform. So I can represent that symbolically like this. Just imagine you have a bar. Let us say that the left side temperature is low compared to the temperature on the right side. So the red here indicates that the temperature is high, greater. So you can see that the temperature distribution is not very uniform. So in these cases, there will be thermal stresses, okay? All right then. Now let us look into the topic of composite bars. We will consider two bars. The first one is steel. The second one can be copper. And these two bars expansion will be considered individually. So first we will consider the individual expansion of steel. So just imagine a steel bar, okay? Okay, now what you are going to do is you are going to increase the temperature, as a result of which there is an increase in length. Okay, we can call that as del L of steel. This is a steel bar. And we will consider a copper bar. And what you do is you expand the temperature of copper bar. And copper bar also expands. We can call the change in length of copper bar as del L of copper, okay? Even though this bar may have the same length, okay, Both the bars may have the same length, but the change in length is going to be different because of different coefficient of thermal expansion. So copper has greater coefficient of thermal expansion compared to steel, so copper is actually going to expand more compared to steel. Okay. But what happens if you put the two together? So, and let us secure them. So you have steel. Okay. The first bar is steel bar, and the second one is a copper. Now, what would happen if you secured them together? Because they are secured to one another, they cannot expand by different amount. They have to expand by the same amount. So the del L is going to be the same. So one equation that comes immediately is, you can see that the change in length is going to be the same for steel and copper. Okay, so this will be our second equation. Now let us see what will be our first equation. Now, if you look at the expansion of steel should have expanded more compared to the individual expansion of steel. Okay, steel should have expanded more compared to the individual expansion of steel. Just give me 1 second, please. Okay, so steel's expansion is greater compared to the individual expansion of steel. So that happens because copper exerts a tensile load on steel. So we can say there is a mechanical tensile load on steel by copper. And what about copper? Copper is not going to expand that much compared to the previous expansion, compared to the individual expansion. That's because steel is actually going to prevent the expansion of copper. Okay, so there is a mechanical compressive force that is exerted on copper by steel. So the mechanical pull on steel is due to copper because copper wants to take steel along with it. And there is a mechanical compressive force on copper because steel is hesitant to expand more. So steel wants to prevent the expansion. So there is a mechanical compressive force on copper by steel. Okay, so for equilibrium, these two forces should be equal. So our first equation will be a load in steel should be equal to load on copper. I can write stress as load by area. So load should be equal to stress into area. So load is stress in steel into area of steel, and that should be equal to stress in copper into area of copper. So this is going to be our first equation. Now, of course, we assume that the cross-sectional areas are different. If the cross-sectional areas are going to be the same, so there will be only one unknown. You just have to come up with just one unknown for one unknown. So stress in steel will be equal to stress in copper. But anyway, you will not be able to solve the equation. Okay. Now you have got two unknowns, and there is a one equation. You just have to come up with one more equation to solve two equations for two unknowns. Okay. So what is the second equation? The second equation is, you can see the change in length of steel should be equal to change in length of copper. So first, let me analyze the change in length of steel, and that is equal to free expansion of steel. Free individual expansion of steel. Okay, and plus steel is tugged along by copper. Okay, mechanically. So there is a mechanical expansion, mechanical pull on steel by copper. So I can write this in the form of an equation. So free expansion of steel is given by the expression alpha delta L. I just have to add the suffix. It is steel plus the mechanical pull on steel by copper. The mechanical pull, the change in length, mechanical change in length is given by the equation PL divided by A. So you know this. So I just have to add the suffix for steel. Okay. Now what I can do is I can write this equation as load by area as stress in steel. So I'll do that. So here we go. So in the next step, the actual expansion of steel is equal to alpha of steel into del T into length of steel plus stress in steel into length of steel divided by Young's modulus of steel. So that's going to be the actual expansion of steel. Now let us bother about the actual expansion of copper. So the actual expansion of copper should be equal to free expansion of copper. Free expansion of copper. And copper is not going to expand as much, right, like the free expansion of copper. So its expansion is actually mechanically prevented by steel. Okay, so there is a mechanical push. When I say mechanical push, I'm talking about the mechanical change in length, compressive length, right? So there is a compression, mechanical push on copper by steel. So let me write it mathematically down. So it is going to be alpha delta L. I just have to add the suffix copper minus mechanical push on copper by steel. So mechanical push is PL divided by A. So I just have to add the suffix copper. All right then. So I can write load by area as stress. This term can be written as stress in copper. So in the next equation, it is alpha of copper into del T into length of copper minus stress in copper into length of copper divided by Young's modulus of copper. So this is the change in length of copper. So for equilibrium, the change in length of steel should be equal to change in length of copper. So I can now write the two equations together. So if I write the two equations together, alpha of steel into del T into length of steel, okay, plus stress in steel into length of steel divided by Young's modulus of steel, and that should be equal to alpha of copper into del T into length of copper minus stress in copper into length of copper divided by Young's modulus of copper. So if the length of steel and length of copper is going to be the same, they cancel out on either side. If length of steel is equal to length of copper, so the final equation can be written as alpha of steel into change in temperature plus stress in steel divided by Young's modulus of steel is equal to alpha of copper into change in temperature minus stress in copper divided by Young's modulus of copper. So I can call this as the second equation. Now in this equation, I know what is the value of thermal expansion. I know what is the value of increase in temperature. I know what is the value of Young's modulus of steel. I know all this, right? So there are two equations for two unknowns. So the first equation, the unknowns are stress in steel and stress in copper. So look at the first equation there. So there you go, right? There are two unknowns. These are knowns. And if you look at the second equation, there are two unknowns. Sorry about that. So yeah, and you can solve the two equations for two unknowns. So, and you can find the values of stresses in steel and stress in copper. Okay. So in the next part of the video, we will see what happens if besides the thermal load, besides the mechanical push on copper by steel and the mechanical pull on steel by copper, what would be the procedure if we also have on top of this, there is a mechanical load that is acting, okay? Physical mechanical load. If the composite bar is physically loaded and also you are going to increase the temperature. So then what happens? Then how do you find? So we will look at that concept in the next video. So I hope this is useful. So thank you all for your patience.